biggest issues I saw is people think 1 divided by 2 is 2. That a half is equal to 2. Or 1 divided by 387 is 387. A lot of people thought frequency and period are the same thing. John, keep your mask on. Thomas, you too. It doesn't affect your ability to breathe at all. So again, and Thomas, keep your mask on. So again, a period is how long in seconds does it take to complete one cycle. Frequency is the number of vibrations or cycles that occur in 1 second. Sometimes this definition will change, and when you do, like, for example, RPMs is a rotation per minute as a measurement of frequency. In this class, we usually do frequency in hertz and not revolutions per minute or rotations per minute. So hertz is going to be per second if we're using the hertz definition. A lot of people thought period and frequency was the same thing, so they said F equals, for example, 2 seconds or 2 hertz, and period is equal to 2 seconds. The only time frequency and period are equal is whenever it's equal to 1, because 1 divided by 1 is 1. Another thing, again, capital F stands for force, lowercase f stands for frequency. Didn't take off, but next time I probably will. Another thing is P stands for perimeter. And T stands for time period, or just period. Should be using lowercase f and capital T. So another thing I took off points for is if you didn't indicate which was the period and which was the frequency. So for example, number 6, again, everyone has different units, or different numbers, I should say. For number 6, if I were to say 4 vibrations in 1 second, so an oscillator makes 4 vibrations in 1 second. So the number of vibrations or cycles in a second is frequency, so this is frequency. So frequency is 4 vibrations over seconds, which is equal to 4 over 1 hertz, which is 4 hertz. Period is equal to 1 over frequency. So I can plug in 1 divided by 4 hertz and get 0.25 seconds. Looking at number 9, suppose the question said an oscillator makes 360 vibrations in 3 minutes. How many vibrations does it take in 1 minute? Well, 360 vibrations divided by 3 minutes is 120 vibrations in 1 minute. So your answer is 120 vibrations. If you did not put a unit or some words associated with the 120, I took off. No answer should just be a number. They should have some unit describing it. How many vibrations does it take? Does it make in 1 second? Well, I know it takes 120 vibrations in 1 minute. So I could have done 120 divided by 60, which would give me 2. However, you could also do 360 vibrations, the original problem, and divide it by 3 minutes is equal to 180 seconds. Which is equal to 2 vibrations per second, per 1 second. What is the period in seconds? Well, the period in seconds is going to be equal to how long it takes one vibration to occur. So skip that for a second and answer part D first. Number D is, or letter D is, what is the frequency in hertz? Frequency in hertz is the number of vibrations in 1 second, so 2 hertz. I can use D to solve for C. Period is 1 divided by frequency. This is the frequency. So 1 divided by 2 hertz is 0.5 seconds. Number 10. A young girl is on a swing that completes 20 cycles in 25 seconds. So 20 cycles in 25 seconds. Well, if we divide these, that tells her cycles per second. So 20 divided by 25 is 0.8, and that'll give you your cycles per second, which is a frequency. So that would give us hertz. So this is for frequency, and thus our period is 1 divided by frequency. This is 1 divided by 0.8 hertz, which gives us 1.25 seconds. Another thing we could have done is look at 25 seconds over 20 cycles. That would also give us period. That's telling us how many seconds per cycle. So period is going to be your number of seconds per cycle, while frequency will be your cycles per second. This will also give you 1.25 seconds per cycle. And we usually drop off the per cycle for period. Number 12 tripped a lot of people up because they did not see that it says centimeters. So for example, if it says 3 centimeters, 3 centimeters is equal to 0.03 meters. You divide by 100 to convert it into meters. Because there's 100 centimeters in 1 meter. So 100 centimeters, you can divide that by 100 to get 1 meter. Number 19 is one I think a lot of people miss. Again, you have to read the problem. Number 19. What is the wavelength of a wave with a speed of 45 meters per second and a period of 10 seconds? Again, everyone has different numbers. So the deal here is we know that speed is equal to frequency times wavelength. This is our speed, and this is our period. A lot of people took the period and plugged it in for frequency. That is not what you do. So we have frequency times wavelength divided by speed, solving for wavelength. Wavelength is equal to speed over frequency. So we need to solve for frequency. Frequency is 1 divided by the period. So 1 divided by 10 seconds is 0.1 hertz. And now we can plug that in for F. 45 meters per second divided by 0.1 hertz. And go wavelength of 450 meters. One question asks you to find the period of a wave, and y'all just solve for F, but didn't convert it into a period. That would be number 13. Number 13 tells you that a wave travels through a spring at 2.5 meters per second and has a wavelength of 1.3 meters. And asks you for the period. You look and you solve for F. F is equal to velocity over wavelength. The velocity is in meters per second, and the wavelength is in meters. But once you get the frequency, you have to convert it into a period. Period is 1 divided by frequency. So if this is frequency, you plug it in here or solve for it first. I think I'm going to do a test review tomorrow. And then we'll have a test Wednesday. There's only one thing I haven't covered yet. That'd be Doppler shift. The Doppler effect. So the Doppler effect, go sit down. So the Doppler effect also applies to light. Does anyone know what the Doppler effect is? Put your mask on. So when put your mask on. When an ambulance is driving towards you versus driving away, it sounds like it's at a different pitch. So let me find it.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of
I would write that down.
a wave caused by relative.
What was it? No, you have to be moving. Whatever is creating the sound has to be moving relative to someone else.
Motion between the source of the wave and the observer.
Relative to someone else.
It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this.
Y'all hear the change in frequency? Did you hear the horn though?
Because you're standing in the middle
Listen
of the road.
to the horn.
The horn to you might sound something like this.
You hear the switch? It's one frequency the entire time.
So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower
Thomas, keep your mask on.
frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or
Elena, keep your
towards
mask
Earth.
on.
As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant, distant future.
It's the reason we know that the universe is expanding right now is we look out at all the stars and see the colors they should be at are wrong. They all appear redder. But going back to this, the sound of this car, do you all hear two frequencies? You hear a high pitch and then switch to a lower pitch? That's an illusion.
The horn to you might sound something like this.
The two honks is not two honks. That's the person holding it down. We hear two because the moment he passes us, it switches to frequencies. We hear two different frequencies, one when he's moving toward us and one when we're moving away. Listen. Did you hear the change in frequency? Again, it's same distance away. The only difference is moving towards you or moving away from you.
What does it mean when a jet
Again, you can clearly hear the change in frequency. So, we say something has been redshifted if it is moving away from us. It doesn't mean that they appear red, though we see some colors, some of them do appear red. It simply means that they're moving toward us. And blue shifted means they're coming. Oh no, red means they're going away from us, and blue means they're coming toward us. So all. Again, in order for you to actually notice these color changes, you'd have to be moving close to the speed of light and keep your mask on. But it's when we say something is redshift, it would mean they're moving closer to the red spectrum. It doesn't mean so. For example, something going from blue to green is moving closer to red. One or two things about it.